already? No. Okay, I still have one more. So we're done with the differential signal, and now I want to spend time to talk about the differential pair. Okay? This is what we have. So if you look at this, how is it different from the one we just learned? You have a bias, ISS. Why do we want to do this? I will explain later. This is called the so-called tail current. But don't worry about this now, right? The one I show you just now is almost useless for a few reasons. We will understand later. For example, you are not able to handle other noise and fluctuation or something called common mode gain. By adding this, it will be more robust. You will see that later, right? But anyway, this is the so-called differential pair. So we want to analyze it. First of all, I still define the output as Vx minus Vy. The input as V in 1 minus V in 2. Differential input, differential output. And again, everything needs to be identical. Left equal to right. M2 equal to M1. So you can imagine process variation, as we've been talking about, right, is going to change the performance of your differential pair. And so that's why, again, for analog circuit, your transistor need to be large. Remember, when you are large, the variation will be smaller, right? It's easier to print compared to the smallest feature, right? They're identical, and we assume the differential signal is applied to V in 1 and V in 2, which means what? V in 1 equals to, when they're differential, how would you write it? Should I write V in 1 equal to V in 2? Minus, very good. V in 1 equals to minus V in 2. Okay? Now, let's assume I don't have small signal at this point, right? Although I say it's differential, but the DC bias needs to be the same because they need to be identical. We're talking about differential, we're talking about small signal differential. Okay? They still have the same common mode. Maybe the best is to draw it in this way. Maybe this is, let's say, negative V in on top of a common mode. And this might be plus V in on top of a common mode. Is this okay? Yeah, maybe this is 2 volts, for example. And that's why they are biased in this way, right? They're identical, right? So when we say identical, not just physically identical, you need to bias them identically, right? This is very important. Also, bias identically. Okay? Now my question to you. At DC bias, when there's no signal, right? When V in 1 equal V in 2, I have a current ID1 here and then ID2 here. What's their relationship? Okay, very good. And what do you say? Identical. Right? This is the first thing you will guess because I keep talking about identical, right? If I have the same device, I have the same biasing, then I think they should be identical because this is just symmetry, the nature, right? If you look at them, the physics are exactly the same. Isn't that I expect them to behave the same, right? No. Left and right has no meaning in the space, yes.
They shouldn't be identical because V1 up is going positive and V2 is going negative, so there should be a difference.
Okay, that's why I say when there is no signal, when V in 1 equal V in 2. Good point, yeah? That it will be the next step, yeah? So now I'm saying that when V in 1 equal to V in 2, that, or basically we say they are equal to 0 in this case, okay? This is confusing. This is about, I'm saying the DC plus AC are the same, Or in other words, V in 1 equals to V in 2 equal to 0. This is for AC. Okay, so I have no signal, right? So all of you are correct. You are also correct. You just say the KCL. So first I know that ID1 equal to ID2. And I also know ID1 plus ID2 equals to ISS. Based on this, what is ID1 and ID2 in terms of ISS? ISS over 2, right? These two add together need to be ISS, and this is ideal current source, right? So again, I don't care what happened because it's ideal, I always have ISS. And now you say you add together equal to me, and then you are the same, then you must be ISS over 2. Okay? Is this okay? So that is the nice thing. This is the picture you need to have in your mind, that under no small signal, they equivalently bias, right? So for example, I give some number now. For example, now maybe this one equals to, let's say 1 milliampere. Right? Let's say this is also 1 milliampere. And then maybe this one is at, let's say 4 volts. How about this point? What would be the voltage, Vy? 4, because it's identical. Or you just look at the current, VDD minus I times RD equal to 4. VDD minus RD times I equal to 4. The I are the same, right? So they need to be the same, okay? Now, then we will start, look at the, now I start applying the signal. For example, I apply this by 10 millivolt. Okay, now I start applying, and this is negative 10 millivolt. Okay, so the total voltage here becomes 2.01 volt. This becomes 1.99 volts. Is that okay? That's what happened to here, right? Now, what will happen to the current just based on your gut feeling? I increase the voltage on the left and reduce the voltage on the right. Based on what you have learned so far, what will happen to this current? Will it increase or decrease or stay the same? Who think it will increase? Yeah, here is we increasing the gate voltage. Okay, who think it will decrease? Why you raise 2 times?
I've been confused.
Okay, sorry, I'm talking about current, not voltage, I'm sorry. So I increase the gate voltage, what happened to the drain current? Not direction, the magnitude, decrease or increase? When I increase the gate voltage, you will increase. You will feel that you will increase, right? Because ID is proportional to VGS minus VT squared, right? And I increase VG, I expect ID to increase. Of course, some of you will say, no, I still don't know what is VS. VS is not ground. I'm not sure. You can say that I'm not sure, right? But on the other hand, on the other side, the VG is reduced, so I expect this one to reduce. And then you try to say, looks like possible, because if this increase, this one reduce, they should still add up equal to ISS. So maybe it's okay. There's such a possibility. But definitely not both of them increase. Can both of them increase? No, right? Because you violate the KCL. They cannot both decrease neither. You violate the KCL again, right? So this is going to change this point. But as you said, when the gate voltage on the left increase, then maybe this one will add, for example, 10 microampere, and this one will subtract 10 microampere. ampere. What you mean by proportional? They need to change by the same amount. Yeah, so that when you add them together, they are still 2 milliampere. Yeah. Okay, have this concept. If the left increase, the right needs to be decreased. Now, if the current here increase, what happened to Vx? Vx will go down, right? Because Vx equal to VDD minus ID times RD, right? So this might become 3.9 volts, for example. And this one will become 4.01 volts. Yeah, I don't think anyone can read this line without watching the video, right? Is that okay? I know it's messy, right? So what is the gain? The gain is V out divided by V input, which is Vx minus Vy. What is Vx? 3.9 volts minus Vy, which is 4.01 volt. Do you agree? That is the difference of the output, right? From 4 to 3.9, from 4 to 4.01. Oh yeah, 3.99, not just better, is I was wrong. Because you need to increase by same amount. Thank you. Sorry, then there will be no gain, right? So let me change it. Still 3.9, and I want to put 4.1. Okay, so this is 4.1. And what is the input? By definition, what is the input for this differential amplifier, this differential pair? 20 millivolts, okay? Or you can say 10 millivolt minus negative 10 millivolts, or some of you want to say it is 2.01 volts minus 1.99 volts, right? You are saying the same thing, right? So which is equals to negative 200 millivolt divided by 20 millivolt, which is equal to 10. Okay, so I use this as a scenario. I hope that you can follow everything on this slide, right? How this number come and understand the real operation. Okay, so I will stop here today. At negative again, typo. Negative 10, right? And if you define it oppositely, define as Vy minus Vx, then it is 10. Good, thank you. So that's it for today. Yeah, but I still here. We still have 3 minutes. Any question on any slide you want me to go over again? Yeah, you feel free to leave, but please. This one.
So the other one. Questions you're asking them with the sign equations. Okay, right, it is. So, what is the differential signal?
Okay, when I say differential amplitude, it means that first, the differential signal defined as the difference of these two signals. Okay, so yes, this differential signal, you call it whatever V equals to V1 minus V2. Okay, so this is equal to 2V0 sine omega t. So TA is asking what is the peak signal of V, okay? And then what is the peak to peak of V?
Different.
Oh, no. When I say the peak, it's just the amplitude. What I'm saying is the amplitude. So you for any sinusoidal. So if you look at this is still a sine wave, right? With a peak that is 230, right? And then so-called peak to peak is 430. Yeah.
Oh, okay.
That can be confusing, but when I say differential signal, it's the final signal when we do the subtraction. Okay. Let me stop recording unless you want to